Hi folks, welcome back to Physics with Captain Rod. I'm making this one to be kind of a short video just to talk a little bit about situations where angular momentum is conserved, or in other words, conservation of angular momentum. And this picture kind of represents the stereotypical angular momentum conservation example. So let's talk about this skater here who's rotating at some angular speed represented by, I guess this, I like to call these squirrely vectors. I'll call this omega 1 here. And this skater has an axis of rotation that looks like this. And this person now has a certain moment of inertia, which is the sum of all the mr squareds, over the entire body there. And with the arms out, right, the average distance to the axis of rotation is relatively large within this picture. So this person right here has a larger moment of inertia than she does in this picture, the picture on the right. Again, the axis of rotation goes right through here. And in this picture, her mass is much closer on average, or at least a little bit closer, I'll say, to the rotation axis. So in the second picture, this person has a relatively small moment of inertia. Now, a very important point to make about this is if we look at a free body diagram of this person, there's a gravitational force down, as usual. Okay. Then there's a contact point right there at the tip, basically at the tip of the skate, and that's going to give us a normal force up. And for all practical purposes, that's about it. And a very important thing to realize is that there is no net torque. No torque on this system. And if there's no torque, that means that the angular momentum is conserved. It's the same in the picture on the left as it is on the picture on the right. And angular momentum for a rotating object like this is really easy to express mathematically. Over here, let's say this angular momentum is the moment of inertia on the left. I'm going to call this one like I1 times the angular velocity on the left. I would call this omega 1. And over on the right, the moment of inertia is different now, so let's call it I2. And you've seen pictures like this or videos and seen that her speed would change. So we have an omega 2. And because of the no torque, because of this, that's what would allow us to equate these two quantities. So basically we would have I1 omega 1 is equal to I2 omega 2. And mathematically what's happening, right, is that this person, when she pulls her arms inward, is decreasing her moment of inertia. So that means that I2 is less than I1. And then when you look at this equality, that means omega 2 has to be greater than omega 1. And we would need numbers here to try to make a numerical example out of this. I just meant this to be a conceptual video here, so I'm going to just leave it at that. I hope that this helps. Have a great day.